Hey, welcome to Global XR. My name is Renee from Alarm Reply, and I'm happy to get started here. So to actually get started, let's roll the video. So many videos, huh? All right, there will be a few more videos, but I thought I'm going to show it to you because I really like the Metaverse video my colleagues created there. And so what we're going to talk about here today in my talk about the future of computing is, of course, first of all, spatial computing and all the things that are related to it with these amazing devices that can sense the world around us, but also things like the AR cloud and, of course, the Metaverse, right? There's no way we could not talk about the Metaverse in these times. And so I'm going to try to unpack that and break it down a little bit. And also, looking at what are some of the enterprise Metaverse plays and also what is the real world Metaverse, which some might call the AR cloud. And then in the second part, we talk about quantum computing, which is also might be related to the metaverse at some degree, because it will help us to, run very large simulations and very large computations, and maybe also true randomness, right? You will learn more about that later on in the session. But anyhow, it's rather two distinct topics, but they have one thing in common: they will change computing forever, right? It will really change the game, what we're looking at. Um, but first of all, let's get started with spatial computing. And in order to explain that a little bit better, we should actually look a little bit back in time and look at the history of computing. And so it all started basically with mainframes, but then later on, for people and their appearance with computers, it was really personal computing, which became interesting in the 1990s or so, when a lot of folks had their first PCs at home, and then later on they became connected with each other through the internet, and that really changed a lot of things and democratized knowledge sharing and enabled awesome communication, which we all appreciate today. Of course, not everything we appreciate today when it comes to social media communication, but definitely it democratized a lot of things and was a key enabler here, right? After personal computing, mobile computing came along, and especially with modern smartphones that had touch input and that also provide a lot of sensor information. For example, GPS providing geolocation and therefore providing contextual information to the user, right? And mobile computing is the dominant computing platform. In fact, certain countries just started with mobile computing, right? They didn't even have PCs. And so after personal computing and mobile computing, we're now entering the so-called spatial computing age, where we have these intelligent edge devices that can sense the world around us, right? And this could be like a HoloLens I have here, which you can hardly see because I'm using Kinect as my webcam. But I'm sure you all have seen a HoloLens. But most importantly, it has all these sensors, right? Cameras, depth camera, tracking cameras, left and right. And so it can sense the world around us to a high degree and provide this spatial map, this spatial awareness to us as developers, but also as users, where we can then see more detailed information powered by computer vision AI in the end, right? But also your mobile phone that you might have in your pocket is also a spatial computing device, like the one I have here. It has a depth camera, but even without a depth camera, most modern smartphones have advanced AR capabilities. So it doesn't even matter if you're talking about mobile form factor or head-mounted device form factor. All of these are spatial computing devices because they can sense the world around us. They can understand your current environment. They can understand, okay, there's a wall behind me, there's a ceiling, and so on, and can make that part of your computation and provide much more contextual information, right? And so, like I said, it really doesn't matter what kind of device you're using. Like here in the video, you can see from Microsoft, from the Mesh announcement video, you see multiple people collaborating. The lady is using a HoloLens. The gentleman there is using, what is it, tablet, mobile phone kind of a thing. So form factor doesn't matter, but they can all collaborate together because they have these spatial awareness with these devices. And that also includes, of course, VR devices, right? Because they have 6DoF tracking. They're aware where they are in the room. And so all of these need to be able to collaborate and combine it. And this is what spatial computing is all about, making the real world, bringing that into the computing. And on top of that, of course, we have the whole notation of this so-called AR cloud, or augmented reality cloud, and also this new way of the metaverse, right? Where we basically dealing with the real world metaverse in this sense here, and I will break that down a little bit later. But basically with this spatial computing devices, like I've just shown you, the HoloLens and all these mobile devices that sense the world around us, it's just the information of the 3D capturing of the environment is just on each of these devices. But if we combine all of that information into a homogeneous reference map of the real world, we could say we're generating a digital twin of the real physical world. And with that virtual digital twin, we can then, anchor content in the real world and can share it with other people and can share it with other devices cross-platform easily, because we're breaking down the barriers between the understanding of each of these devices, but they have this common reference map. And this is what the real world metaverse is all about, this digital content layer on top of the world. In a sense, the real world metaverse, or the AR cloud, whatever you want to call it, is providing what the internet was providing for the PC, for the personal computing area, the spatial web, the web 3.0, as some call it, or the real world metaverse, is providing the same capabilities to the spatial computing age what the internet was providing for the personal computing age. It provides us this connectivity and all of that. So let's talk a little bit about the metaverse. And we have our entity here that has all the knowledge. So I just looked at Wikipedia and took the definition of the metaverse there. And now we will break it down a little bit later on. But basically, they're pretty much on point here, right? It's all about that you turn these experiences that you have today, or the internet that you have today, and make it a 3D experience. So some call it the immersive internet, or some others say, okay, if you're visiting a website today, that will become a 3D space in the metaverse later on, right? But in a sense, what is very important here is that you also have, as a person, you also have a virtual presence in these metaverse spaces. And that is also a point I'm going to talk about later on. But for now, we got to think about, okay, we have our real world, and with the metaverse, I have this digital twin of the real world, and I can merge those together, right? I have this digital content layer on top of the real world. And you could even break it down in terms of different technologies. And we broke it down into 7 different layers, as we call it, the 7 layers of metaverse. And so at the bottom, you have the infrastructure, right? You have the connectivity, 5G, Wi-Fi 6, and so on, which are very important. And on top of it, you have the human interfaces aspect, also super important, right? A user might use a mobile phone, others might use a HoloLens, head-mounted device, whatever it is. And then also an important factor is, of course, the economy. And we see a lot of uptake here with decentralized approaches like blockchain and so on for, exchanging assets in these metaverse world. And then, of course, the whole spatial computing powered by computer vision AI that can provide us more contextual information about our current environment. And we have the creator economy. Basically, if you look at Snap or Facebook or Meta, all these creator tools they provide, where everyone can basically become an AR filter creator, right? Because these tools are so amazing and very well useful. Or look at Roblox and other things, right? Where everyone can become a creator, basically. Then you have discovery, of course. You will have advertisement network, social media, and so on. And the whole different experience layer on top could be games, could be enterprise metaverse spaces, or could be consumer virtual metaverse spaces. But these are like the different building blocks or layers of the metaverse, if you will. And it will have quite some potential, hopefully. If you look at some of the predictions from, for example, here the quote from Bloomberg, they basically estimate 800 billion by 2024. So this is in 3 years, and of course that's quite a lot of money. And so we're all part of that journey, and so we're in a good spot here, I think, in our industry there. But it's already providing value. And here I have some graphics or some data from Microsoft and mixed reality solutions. And you can see remote assistance is, of course, providing already a lot of value, especially in these crazy times. But also, if you look at manufacturing training solutions, like the Lockheed Martin case is pretty impressive, where they have 90% time saving because they can use a HoloLens and a spatial computing overlay on top of a physical object and can get their work done much faster, right? So it's already providing quite some impact. And like I said, basically everyone has such a device in their pocket. I recently looked up the data again. It's around 2 billion devices that either are Android AR Core devices or iOS AR Kit devices that have these advanced AR capabilities already built in. And I took the data also 2 years ago, and it was half of it. So it was 1 billion. So basically, like I said, most of us already have a spatial computing device, which we might use every day, right? And it doesn't have to be a HoloLens or another head-mounted device, but even your mobile can do quite some impressive things already. And everyone will use it. Here's some numbers from Snapchat, which is estimating that in 4 years, 75% of the current users of social media will also use AR experiences every day. But of course, that also includes AR face filters and all of that stuff. And you might say, well, that's quite a high prediction, 75%. Again, that also includes things like Google Lens and whatnot, right? So it's a wide definition of AR here in the statistics. But also, you have to say Snap and Snapchat is actually delivering on their promises, and they just crossed 1 billion in revenue, and they reached recently 306 million daily active users on the Snapchat platform, right? And so it's coming, and it's already here, in fact. So if you look at some of the Metaverse plays or some of the experiences, it's already here basically with the Metaverse. It's the whole definition, the term, as you might know, it started with some science fiction novels like 30 years ago, but we already have implementations of virtual Metaverse spaces already with these large online gaming works like Minecraft, Roblox, Fortnite, what have you. These are all these virtual worlds, large gaming worlds where users or gamers are represented as avatars, and they can meet and play games in these virtual spaces with various input devices, which is very important, right? So it's not just for VR. And then we have companies like Facebook that are, going full in and rebranding themselves to, for example, Facebook now being Meta, right? And they're working on what I call the virtual Metaverse solutions. And basically, you have these virtual worlds for Meta. It's called Horizon Worlds, where you can meet your friends instead of like going on Facebook.com and browsing through the timeline. You can meet all these folks together in these virtual worlds, exchange information with each other, and you yourself are being represented as an avatar, of course. And that will work not just on a VR headset like Meta's Oculus Quest, but also on standard devices like mobile, a PC, and so on. And that is very important because it needs to be able to be work cross-platform and everyone taking part of that, right? But this is more about this virtual Metaverse play where you're fully inside these kind of virtual worlds. And in fact, there's already quite some interesting things already happening when we're looking at the economic perspective here. And I took 2 screenshots last couple of days here from some news announcements. And so, for example, there is a Metaverse, virtual Metaverse land. I think it's called Decentraland. And they sold for 2.4 million US dollars virtual real estate there. So basically a virtual shopping center, kind of a place where you can buy clothing, fashion street, that's how it's called, right? So 2.4 million for a virtual real estate shop. All right. And the other screenshot here is from the folks at Admix that recently sold a virtual ad billboard in another metaverse world, which is called Somnium Space. They sold a virtual billboard for almost 70,000 US dollars, right? Which is quite a lot for a pure virtual billboard. But anyhow, I guess someone paid for it. And you might say, well, that's crazy, but look at this. Just recently, just yesterday, in fact, a virtual boat was sold for 650,000 US dollars. And of course, that's all done with coins. I think with Ethereum mostly. So I guess someone has a lot of Ethereum still left and just wants to buy some stuff. But yeah, this low poly boat sold for 650 thousand US in another virtual world. Did I hear someone saying there's a new .com bubble in the making? I don't know. But anyhow, like you have these virtual metaverse worlds, right? Where a lot of things are coming together and there's money in the play already. So this is mainly for consumers. But if we're looking more at another angle, for example, with NVIDIA, they're also working on metaverse solutions, which they call Omniverse. But it's quite a bit different because Omniverse, for example, is really aimed for professionals that build digital twin solutions that work with simulations or 3D tools. And so basically your 3D toolings like Maya, whatever, they will have connectors, they will have plugins into the NVIDIA Omniverse, right? You will also have an avatar system, of course. But most importantly, what I call it is the workplace metaverse, right? You have these connectivity between all these different tools and be able to get your work done in a better way. And that is pretty impressive. And what NVIDIA is doing there is definitely very innovative. But also other companies are working on it. Already mentioned Snapchat. And Snap is also working on their own, which they call Snap connected lenses or local lenses. And this is an implementation of the real world metaverse, right? Where I sense the real world. I use my spatial computing devices to get this digital twin of the real world. And then I can make the real world my canvas, right? I can share it with my friends via connected lenses here and have these local lenses experiences where I can, do a lot of impressive things. And I don't need any QR code. I don't need GPS. The real world is my marker where I can put content in it. And of course, here you can see the photo with Katherine Harris, where she's wearing the spectacles, the head-mounted glasses from Snap, which are also coming together quite nicely. So a lot of movement there is like in terms of hardware, but also especially in these kind of real-world metaverse solutions. And of course, there's another player here which I want to mention is, of course, Niantic. Right, you have Niantic with their Lighthouse platform, and you might know Niantic from games like Pokemon Go, Harry Potter, and also the acquisition of 60 AI. And Niantic already has a large metaverse, with lots of data about the world collected from all these various Pokemon Go players, right? And they recently just had another funding round where they got 300 million at a 9 billion valuation. So Niantic is valuated at 9 billion US dollars, right? And they're going to work and build the real world metaverse. That's what they just announced. And here in the video, what you can see here is a demo where I took their ARDK, their augmented reality development kit, which is part of the Niantic Lighthouse platform. And I tried it out in my garden. If you have seen some of my videos before, I'm sure you would all feel very familiar if you visit me in person in our garden here. But what you see here is just running on an old Android device. And I can tell you, if I like the meshing, like the spatial mesh it generates here is so good. Like 4 years ago or something like that, I had to use a HoloLens 1 to get such a quality. Of course, the HoloLens 2 still provides better quality, but this is comparable to a HoloLens 1 spatial mesh. And it's pretty good. And it runs on basically any mobile phone. And it doesn't even have to have a depth camera. And so, long story short, Niantic, all the other companies are working on these real-world metaverse solutions. And of course, also Microsoft with the Azure Spatial Anchors, which you might have seen in this demo video here I made, where I'm taking basically old video footage and put it in front of the real world. So I'm basically embedding this video in the real-world metaverse, if you will. And I provide this kind of video portal into old times, right? Where I can look, okay, how was it looking in the old days? And this is without any GPS. This is without any QR code, no fiducial marker being used. The real world becomes your marker because we have the digital twin of the real world. We have the real world metaverse. And this is where we can put anchors in. This is where we can put spatial anchors in, which we can share with each other. And we can share it over time, meaning we can persist it and load this information at a later time. And this is what I'm really excited about, is this kind of real world metaverse. And also Satya Nadella put it actually beautifully here in this statement, where he was basically saying is increasingly as we embed the computing in the real world, you can even embed the real world in computing. I think that says it really nicely what the metaverse is all about. It's like we make the real world part of our computation, right? And so it's no wonder that Microsoft is, of course, also investing here with the Azure mixed reality stack, like Azure Spatial Anchors and all the other stuff I just mentioned, but also, of course, the mesh platform, the mesh development platform. So what is that? Well, Microsoft Mesh, you probably have seen some of the demos. You might have heard about it. I'm sure some of you already experienced it themselves. And what you can see on the video is just one implementation of Mesh with the HoloLens Mesh App Preview, which I tried out with my colleague Jesse, who is living on the west coast of the US. And so I live in Germany, which means we are 9 hours time zone away. And as you could see, when we do the high five, there's no delay really. And so what Mesh allows us to do is we can build our own applications on top of the Mesh platform. So the Mesh takes care of all the heavy lifting under the hood, like the multi-user sync, that you don't have a lot of delay. You can have model sharing, model loading, also with Azure Remote Rendering. You can anchor these with spatial anchors and what have you. And all of that is supposed to work cross-platform, right? So currently HoloLens, PC, but it's supposed to be also working on VR headset like Oculus Quest, mobile phone, and so on. So it's all about like having a different cross-platform devices being able to connect here. And again, like building metaverse applications with Mesh will also allow us to have connectivity between those, right? Because we have a common standard layer which we can build on top of. And it's still in its development, of course, and I hope we can talk a little bit more about it next year. But yeah, it's an exciting time. And also, you might have seen at Ignite, they showed a Mesh for Teams, which I call a gateway into the metaverse, because we have 250 million users worldwide that use Microsoft Teams. And if we're bringing this kind of Mesh capabilities, this Microsoft Metaverse solution into Teams, we of course go where the users are, right? And so as you can see on the demo video, you can create these virtual spaces, like these corporate metaverse spaces where you can meet each other, represented as avatars, and exchange information and have that all persisted all over the place. But you can also use that actually as your webcam representation. So instead of turning on your webcam, you can use this avatar as your profile. And so in your meeting, you would actually talk as an avatar and not as a photo or video, right? Which is also could be pretty interesting. And so that actually means like this kind of virtual presence I mentioned is highly important, right? This is how we will be seen in this metaverse world. And the challenge, though, is currently, like each of these platforms has their own like look and feel and metaverse and avatar system. And so you have, for example, like here is an Outspace VR avatar next to the Snap one, and they already changed quite a bit. And if I now go to Meta and sign up for Horizon Worlds, I have to create another avatar, right? So you have all these different avatars all over the place, but you are you, right? And so just like you take your profile picture today with you, you want to take your avatar with you. And this is where also blockchain and maybe NFT could play a role here, right? You can decentralize the ownership basically, or basically, no, you own it yourself. It's not like Meta or Microsoft that basically creates the avatars and owns it, but it's actually really decentralized, and so you control it, right? And so that might be an interesting point here. But avatars will be, of course, the way to go until we might have holoportation, like 3D volumetric video, which you can see here in our HoloBeam solution, which we have been developing since 2016 or something like that. And here you see we actually also created a little Teams plugin, which actually is not a Teams plugin, but it's just a virtual webcam driver. And so I can select my HoloBeam output as a webcam input for Teams, Zoom, whatever it is. But of course, there's still limitation in terms of hardware accessibility and so on. You needed a 3D camera like a Kinect. And that is, of course, still a challenge. But, with computer vision, AI, depth estimation, all of these things become much more streamlined. And I'm optimistic at some point we might also be worked together in a 3D volumetric video in these kind of large worlds. Of course, a big limitation is also computational power, bandwidth, and so on. But these things are all coming together now. To wrap it up in terms of the spatial computing part and the metaverse, we could also categorize it a little bit. And this is what I tried to do here. We could say, okay, consumers will mainly use these virtual metaverse world, right? But of course, they will also use some of the real world metaverse solutions like Niantic and folks are working on. And but I think so even more so that will be important for enterprises, right? Like this real world metaverse, like I mentioned, this digital content layer of the world. And think about IoT sensors, right? In a factory, you can locate them. You have this IoT layer, and you have this real-world metaverse layer connectivity compared with various sensor information. And so I think that will play an important role for enterprises. But also these corporate metaverse spaces like Mesh for Teams and so on will also be highly interesting. But anyhow, the whole metaverse term in itself is so fuzzy at the moment. And it's like a qubit. like a quantum computing bit, right? It's like being in multiple states at the same time, kind of. So it's really a little bit fuzzy and uncertain, which brings me to my next topic here about quantum computing, which might also have some relation to these large online metaverse and will help here with the computational power it provides to run large simulations and a couple of other things in the next couple of years. And true randomness, right? We can get true randomness with quantum computers. So what is quantum computing actually? Well, quantum computing, first of all, will make today's unsolvable problems solvable in linear time. Of course, not all of them, but many of these very computational, expensive problems will be solvable in linear time. And so it might be the most disruptive technology that we're about to see in the 21st century. Currently, in terms of the hardware standpoint, we're in this kind of mainframe area we had in the 1950s or so, right? You have these large machines with very little computational power. IBM, for example, just set the new record with a new quantum computer that has 127 qubits. But also one thing you got to keep in mind, like these quantum computers, the hardware is not going to replace your classical computer, right? There will still be semiconductor-based silicon in your mobile phone or whatever, right? This won't be a quantum computer anytime soon, if at all. You should think about a quantum computer is an accelerator. Similar like a graphics card is a graphics accelerator, a quantum computer is an accelerator for certain computational problems. And that's where we will see a lot of breakthroughs, though, with these unsolvable problems that I mentioned. And also, it's new software. And what I mean here is it's a thing called quantum-inspired computing, where we take quantum computing algorithms, like algorithms that you write in a way that they would run on a quantum computer, and then you can execute and simulate them on classical computers, but they already provide quite some interesting benefits here, which I'm going to show you an example later on. But before we do that, let's make sure we're all on the same page and we all know what is actually quantum computing based on. So quantum computing is based on quantum physics, like or quantum mechanics, which is a discipline of physics. It's around 100 years old, a little bit older than 100 years, 120, 140 years or something like that. And so quantum mechanics describes how the smallest particles that we know behave in our universe. So we're talking about atoms, ions, or subatomic particles like photons, electrons, and all of that. And at the smallest scale, certain phenomena occur: superposition and entanglement. And we can take advantage of those and use those for computation, right? So if you look at the slide here, you see in a classical bit, in a digital bit, it can just be 0 or 1, off or on, right? But in quantum computers, we're working with qubits. And a qubit as a physical representation could be a photon. It could be an ion. Actually, trapped ions as an implementation of quantum computers are quite popular, right? So basically, your qubit is an ion, a trapped ion, or again, a photon or whatever, or atoms. It's really the way different models are approaching here. But in a GIST, what is important is your qubit cannot just be 0 and 1. It cannot just be the digital representation, although it could be, right? But it can also be in a superposition state, which allows to basically represent multiple states at the same time. So a qubit can be 0 and 1, and it can also be 0 and 1 at the same time when it's in superposition, right? That's a little bit complex to wrap your head around it, but just assume that really works. It was proven in experiments, right? And then you can do another step. You can entangle multiple qubits together. So you have your qubit in superposition, and then you can entangle another qubit together. And so then you have two qubits which are entangled together. And the awesome part is, since one qubit can represent and store multiple states at the same time and compute multiple states at the same time, if you entangle another qubit, you're actually adding an exponent at your computational power you have at your hands. And so basically what we have with superposition and entanglement with these qubits, we get massive parallel computing. And that is, of course, very, very useful. But you might say, entanglement, what is that actually? Well, it is you put these qubits together, and if you make one change to one of these qubits, the other one will show the same changes, although they are not physically in the same location, which is crazy, right, if you think about it. But that's really the case, and it was proven in experiments since then. Einstein actually was still skeptic about quantum mechanics before he died, because all of that was just theory when Einstein lived, and since then all of that has been proven. Einstein actually called entanglement the spooky action at a distance. There's something in the play we just don't know yet, right? And so here's a quick showcase where they actually have proven entanglement with this setup with a photographic proof that was done in 2019. So basically what you see here is this apparatus, which basically is a laser that is shooting photons. And in this case, we have two photons which are entangled together. So our qubit is a photon and they are entangled together. You shoot them from here to this splitter, and one photon is sent to the left and the other one goes straight, right? But they're still entangled, although they are physically not in the same location anymore. And you make a phase shift to one, like basically rotating it, and the other one does not get the phase shift. So just one that goes to the left gets the phase shift, and then both are measured at the end. And as you can see, this is the first one, this is the second one, and both get rotated, both have the same phase shift applied. Although just one got it physically applied, the other one was entangled in different location, had the same phase shift, right? Spooky action at a distance. We'll see. It's just we'll see, you know. But anyhow, the thing is, the most important part is we can take superposition and we can entanglement and build some pretty amazing things with it and have this power of computation at our hands, which is incredible. And some of the key areas we are seeing with a quantum optimization and quantum machine learning here and quantum security are really providing quite some impact already today. Like I said, the hardware is still in an infancy, so it's still building up, right? You can actually do some pretty impressive things already with certain specific problems, even on those limited hardware capabilities. But the large power is really when we're talking about quantum-inspired computing, where we can take quantum algorithms and run them on classical hardware, which simulates quantum mechanic behavior, of course. Key area, quantum machine learning, for example, is also super relevant, where we actually see some pretty impressive things. I just recently talked in my Qubits video series with an expert in quantum machine learning, and he basically was saying he's using it for image classification. And so he has his neural network basically for image classification, but one of the later layers, it's a hybrid approach, if you will, is represented as an quantum layer. And that provides much better results. So it's more higher accuracy and faster, even with this small hardware we have available today. Why is that the case? Well, we have this qubit in superposition. It has this probabilistic nature, right? It can be multiple things at the same time. So we can represent that probabilistic behavior a little bit better, and the randomness, if you will, right? And so that might be the reason, but it's still, of course, very much research that is ongoing to find out. And secondly, quantum security, and I want to dive a little bit deeper into that one, because it is two things. Quantum security provides us an opportunity, but also at the same time, it can also be a threat. But let's talk about the opportunity first. So with quantum mechanics, we have certain principles that if you have a qubit in superposition, in this case, we would use photons here. If you have it in superposition, but you need to measure it at some point, right? You need to basically get the value out of it. And when you do that, it collapses from superposition. And so you will always know if someone tried to look at your data. And this you can take advantage with quantum key distribution. So here's a scenario. Alice and Bob want to exchange secret information. In order to do that, they first initially exchange a secret key, a symmetric key here. And then you have this intruder, Charlie, who wants to steal the key. And so he steals the key here, but Bob will know that he looked at the key because, it dropped. He measured it, basically. Charlie was measuring it, so it collapsed in the state. And so Bob will always know, okay, someone looked at it already because, the state collapsed, basically. So what they do is they repeat the process all the time until they finally have successfully exchanged the key with each other. And then they can use that to encrypt the data and just, send the data encrypted over a normal channel. And so quantum key distribution, super interesting stuff here, and is providing already quite some impressive results. Recently, they broke a new record in Japan with a 600-kilometer long quantum key distribution channel. Because you have to imagine it's fiber optic, but you cannot have a repeater in between. Because if you have a repeater in between, it will collapse the state again, right? So that won't work very well. So therefore, there's even crazier experiments. Well, I say crazy, but it's actually impressive. They're using satellites, Earth-orbiting satellites, and all the big space agencies, like China, is also very heavily investing in that. But also the US, the NASA, and the European Space Agency, and all of them, they're all looking into having quantum key distribution satellites. So you have a satellite orbiting Earth, and instead of you're having a wireless connection basically for exchanging this quantum key distribution, If you do that on Earth, you have a lot of atmospheric scattering, right? But if you do it from the satellite, you have a direct line typically, and you have much less atmospheric scattering, which will, of course, affect your quality of the data. And like I said, you cannot have a repeater in between because this will break the whole idea about it, right? But anyhow, pretty impressive stuff with quantum key distribution backbones already happening. Another important factor is, of course, true random number generators. I recently saw a tweet here, which I copied a screenshot. You know, in the top right, you can see it. It's such well explained. So it's a screenshot or a photo of a book. And on the left-hand side, you can see the typical random generator we use in our computers, which are just pseudo-randomness, right? They're not true random. But if I'm using quantum mechanics and, you know, quantum physical attributes, I can get true randomness, right? And this is what you see in the right hand. You cannot really see a pattern here. And that is, of course, also maybe useful for, you know, large metaverse world where you might need true randomness. Who knows? But super, super important is like to have true randomness for cryptography, because they are all based on, you know, true randomness. Which brings me to this part here, Q-Day preparation for via crypto agility. So what is Q-Day? I will explain that in the next slides with a nice graphic. But basically, Q-Day is the day when quantum computers will be powerful enough to break current day's cryptography. And that will happen sooner or later. And the challenge, though, is that some companies might have, for example, all their certificates, all their keys, and so on, distributed in multiple servers and, you know, spread out all over the place. And that is, of course, challenging if you quickly need to exchange these certificates because they were broken. And so a couple of other things are also part of this called crypto agility or DevSecOps, that you make it much more streamlined, right? And you can basically adopt before risk arises. And that is very, very important factor that companies really need to take action now and prepare themselves so that it can quickly actually, for example, change the current cryptography algorithm with post-quantum cryptography algorithms that are resilient to quantum attacks like Shor's algorithm and things like that. But what am I actually talking about with this whole Q-Day thing, and when is that? So again, a Q-Day describes, by the way, some call it Y2Q. If you're old enough, you might remember the millennial bug and Y2K. And so there's the Y2Q also, or Q-Day, which describes this day when there's quantum advantage, when we will have powerful enough quantum computers that will break a current day's cryptography. You have to know that today's privacy and digital security and all of it is based on asymmetric keys or public-private key scenarios, like RSA is one algorithm there. And so every HTTPS connection, you know, if you're exchanging messages or if you're doing a bank transaction, all of that is, of course, secure and encrypted. And today's encryption, like RSA, is based on prime factor factorization, so prime numbers. And if you want to factorize those, it's very, very hard and it will take a lot of time. And here on this graphic, you can see on a good computer, it would take more than 300 trillion years, which is older than the Earth. If you use a supercomputer, you might get to the age of Earth if you want to crack an RSA 204080 key using prime number factorization. And with a quantum computer, you can do that all in parallel. And that's, like I mentioned, you know, you have this massive parallel computing. And so you can, you know, try out multiple things at the same time. And that is, of course, very useful for these kind of attacks. And there's an algorithm called Shor's algorithm that can crack these RSL algorithms with a 6,000 qubit processor in 2 weeks. And that might happen in the next couple of years, in fact. IBM, like I said, has 128 quantum computer at the moment. They say next year they will have 433, I think. And then in 2 years, they say they will have a 1,000 qubit computer. If you look to the lowest here, if you have a 20 million noisy qubit computer, it will take 8 hours to crack SR 204080. If you have a quantum computer that has 4,909 stable qubits, which is still quite a little bit like a lot, so 4,000 stable qubits will break us at 204080 in 10 seconds, right? So we're getting there. The question is how long it will take. Expert says it could be 5 to 30 years, at average around 15 years. But as you know, right, exponential breakthroughs happen sometimes, and it can quickly change the game here dramatically. And so that's why I'm saying, like, got to prepare now. Think about, like, you know, how can I quickly exchange my current cryptography that is weak for quantum computers with new cryptography algorithms that are being developed currently called post-quantum cryptography algorithms, so that you prepare. And also keep in mind, like a lot of governments in the world are basically saving all of the data that we have, that we're exchanging today. There are certain entities that save the whole internet and large data centers, right? And like in 10 years, they might just crack open everything, right? Because they have the quantum computers ready then. So always keep that in mind. But anyhow, let's look into quantum inspired optimization as a last part here, because looking at the time, we got to wrap up here quickly. Quantum inspired optimization, already explained that in general, an optimization problem is always about, you want to find the global minima, the cost saving function, the energy function, right? You want to get the maximum output by putting in the least amount of energy into your system. And there's a lot of things you can do there, and you can already achieve impactful things with quantum inspired optimization here. So basically, you can implement optimization algorithms with quantum computing algorithms, and then run those on classical hardware and even get better results than classical optimization algorithms. Use cases are, of course, public transport scheduling, workforce management, fleet management, vehicle routing, all of that. Of course, material science and especially life science and drug and protein discovery is very important. Like, for example, protein folding. In fact, last year there was a research paper where they were using quantum computer for folding proteins with the SARS-CoV-2 virus and so on, right? And so, I mean, in the end, what we're dealing with in the real world, in our real universe, we're dealing with quantum chemistry, right? And so if you can simulate that closer to nature with a quantum computer, much, much better, of course, right? Second, of course, we also, a fourth one here on my slide, not the second, the fourth one on my slide is financial optimization. Of course, if you look at like, Monte Carlo simulations and so on, portfolio management, asset pricing, risk analysis, all of that is very, very useful with quantum computers. One use case we developed at Reply was with a client that has a large energy grid. It's a large energy grid provider, and they have a certain workforce. They have 20,000 field service workers that have a certain route every day where they need to go maybe and fix a transformator station or visit clients and help them whatever energy grid issues might arise. And so they have a certain schedule. And if you're familiar with computer science, you of course have heard about the traveling salesman problem, and that's of course what they're facing, right? So you want to optimize the route that they don't spend a lot of time on the road, but actually have more time at the clients, and you don't drive crazy routes through the country. And that can be, of course, is a big optimization challenge. And what we did here is we developed our own optimization solver called MegaQubo. It's quadratic unconstrained binary optimization. And this is a quantum algorithm, which we then put the problem into this formation so that it fits into the Cubo technique, if you will, and then run that on a large GPU array. So not on a real quantum computer, but on a quantum simulator, which runs on a GPU array and simulates how a quantum computer would behave. And with this, even with this, we get 20% time reduction. Like, this is a ton of money that can be saved here, right? So 20% time reduction for 20,000 field service worker by using quantum-inspired optimization, running, of course, certainly on a large-scale quantum, on a large-scale GPU array, but still good stuff, I would say. Also took part in the Airbus Quantum Computing Challenge. This was all about how can I optimally load a plane. Like, as you can imagine, lots of constraints with plane loading. Like, okay, I have a certain center of mass. I want to save fuel, and a lot of other constraints. Very complex optimization problem. And quantum-inspired optimization is actually providing quite some benefits here already. We also have some papers out there. And if you want to learn more about quantum in a general, I would recommend check out my video series, which I'm doing since last year, which is called Qubits, where I'm inviting true expert guests to come in and talk about certain quantum topics, but in a short way, 10 to 15 minutes, short videos. And the goal is really to make it approachable for everyone, and not just for folks that have a PhD in physics and things like that, but really making it approachable for everyone. And so check it out if you want to learn more about quantum computing. And well, with this, I'm pretty much at the end here of my session. To wrap it up, we saw different things, of course, but spatial computing with the real-world metaverse is, of course, providing us this kind of connectivity with all of us together with different devices, with the real world. We embed the real world in computing, and that is super exciting. And then with quantum computing, we get the powerful computational power to solve really complex problems. And I think especially quantum computing will help us to solve the big challenges we as humans face today, right? You can run large climate simulations. You can run a lot of interesting things, like I said, protein folding, fertilizer development. All of that can be accelerated much, much better with quantum computers. And so it's an exciting time to be alive, where we see all of this sci-fi tech we just saw in Star Trek and all the sci-fi movies. It's becoming a reality, right? And with that, I wish you all a great Global XR conference. There's a packed 3 days ahead of you. There will be amazing talks by a lot of my friends, in fact, and but also amazing other speakers, and you really want to check out everything. Thanks for having me. If you want to connect, feel free to connect on LinkedIn, find my name there, or you see my Twitter handle here, maybe on my jacket or here on my slide. Feel free to connect. And again, thank you so much. Have a great day. I'm out. Bye-bye.